Hi, welcome again to my video. This is video number 20. Right, we begin the beginning of chapter 5. Yeah? Vector field. Vector field. Right, so what is vector field? So let me give a brief introduction on what we are going to do in this chapter. All right, so basically we will deal with calculus of vector field. You call it as a calculus of a vector field. Vector field. So what is this? We will deal with line integral, then surface integral, then connection between a single integral, double, and triple integral. So meaning that we will deal with Green theorem, deal with Stokes theorem, Green theorem, Stokes theorem, this is Stokes theorem, and divergence theorem. Okay. Let me introduce first what is let me give the definition of vector field. What is vector field? Definition of vector field. Okay, so let D in some domain in R2 xy. So a vector field on R2 is a vector function basically. It's a vector function f that assign to each pair xy in D, a two-dimensional function, f xy. Okay, so we write this function f xy as pxy I plus qxy j, where p and q are component of the function f. Component of f, and it is a scalar of f, and they are called a scalar function. They are a scalar function. Scalar function. And then this is for 2 dimension. For 3 dimension, I'll give you another definition. Let's say let E is subset of R3. R3 means in the space XYZ, right? Vector function, VF vector function on R3 is a function. Okay, a vector function on R3 is a function f that assign to each point x, y, z in E a 3-dimensional function, vector function in E to a 3-dimensional vector function. F x, y, z. So that's it by definition, and we write this as in the case of 2-dimensional. We write this function as f x, y, z. This is equal to p x, y, z, I plus q x, y, z, j plus r x, y, z. Okay, and again this PQR is a component of F, and scalar function. Okay, now let me describe how do we sketch the vector function. How do we sketch this vector function? Sketch vector function. Example, let's say you are given f as a negative y I plus x j. A simple. Complicated one we cannot do anything. We have to use computer. But now for the simple function we can describe this. So select any point xy. You must select any point xy, then see what happened to f. Okay. For example, I choose let's say this is 2 dimension, so we have x and y. All right. So pick up any point there. This is what is it? Here, this is 1 0. So you can pick up 1 0. So you can pick up 0 1. This is x0 0 1. You can pick up here as minus 1 0. You can pick up here 0 minus 1. You can also pick up 1 1, here minus 1 1, and so on and so forth. And then to make it a little bit bigger, then you can choose, let's say 0 2 0, 0 2, and so on. Okay, this is just example of this point. So what happened to f with this? So we have for f, so y is 0, so x is 1, so f is in this case equal to j. In this case f is equal to y is minus 1, so minus I, in this case f is equal to minus j. Okay, substitute this into here. Here is y is minus 1, so you have here you have f is I. Here you have f is 2j. Here you have f is minus 2i, and so on. Okay, and if you realize here the magnitude of f all are equal to 1. Alright, so how to plot here the point 1 0. Right, so you pick up point 1 0 here. Look at the vector f. F is j, magnitude 1. J means it goes up 1 unit, goes up 1 unit. This is j. Done. Then next point we choose, let's say 0 1 0 1. This is 0 point. So look at our function. This is negative I. So at this point 0 1, so we have negative I. So it goes to negative to this side I. And next we choose minus 1 0. Minus 1 is 0 here. Give him f, negative f. Negative f means opposite of y. So we have that. Okay. And 0 minus 1. 0 minus 1 is here. You got positive I, f. So that gives us 0 minus 1 that direction. Okay. And if you look at other point, let's say here we choose 2 0. 2 0 we have 2j. 2 0, this is 1 0. 2 0, let's say make it a little bit longer. This is 1, this is 2, so this is x. So 2j, so it goes 2j, magnitude 2. That. Then if you proceed this, you choose this point, let's say 0 2, you got that. If you choose a point here, it goes, should be longer than that. If you choose more point here, it goes like that. Okay. If you choose point 1 1 here, it will goes like that. No, so what you can see here, this is, you can imagine that this is a circle. You can imagine that this is a circle. You can imagine that this is a circle. Okay. So the vector field at this point, basically is a tangent to that circle. You can see here, this is the tangent to that circle. Here you can see the tangent to that circle. Here it goes tangent to that circle, and so on and so forth. So this is the vector field. So you can imagine the vector field is like if you learn in the school that like a magnetic field. Like it won't cross. It won't goes like that and like that. No, this will not happen. It's just in the same direction again and again. Okay, so this is just example how do we sketch the vector field. Now let me give you another example. Let's say we have in 3 dimension x, y, z is equal to zk. Let's say we have this. Okay, so how do we plot this? So again, we choose a point x, y, z and see what happened to f. Okay. So of course, in this case, whatever value of x, y, it doesn't change y. Doesn't change z. So you can choose z is let's say 0 0 1 0 0 minus 1 and 0 0 2 0 0 minus 2. Then also other combination you can choose also, for example 0 0 1 1 0 2 1, what else, 0 minus 1 1 and so on. You can choose any, and then you can change here as well, 1 1 1 1 0 1 and so on. Okay, and see what happened here. So if you look at it carefully, at z equal to 1, if you choose z equal to 1 like this, z equal to 1, so basically it's on xy plane, it's just on xy plane. So here z is 1 here. If z is 2, the magnitude becomes 2, so it goes higher. So for z equal to 1, it goes like that. For z equal to 2, it goes higher. 2, because magnitude is 2 here. So for other as well, so you just have something like this. Just on perpendicular to xy plane, perpendicular to xy plane. And then for the negative, you may have this is negative 1, so you have that, then you have like this. And so on, and as well as this side here. Right, so you have and so on, perpendicular to the xy plane. All right, so that's about the vector field. Now I'm going to define the gradient vector. Okay, what is the gradient vector? I'm not sure we have made this thing before. Gradient vector field. Okay, so we define this del as a del f del x, del x del y del z. It is an operator, differential operator, and this is differential operator, and it is a vector. This is component of x, component of y, component of z. So if we choose or impose or attach a function, a scalar function, let f be scalar function, f is a function of x, y, z. All right, so if you attach that operator del f, so del f, that give us vector, because this function f is a scalar function, del is a vector operator, so that give us del f del x del f del y del f del z. Okay, remember that. So if f is a vector function, we cannot have this. We need some operation. That one is different things, either curl or divergence, but so you cannot have. So in order to have like this, f must be a scalar function like that. So don't write this. Okay, I'll give you an example of how do we apply the gradient function. Example, let f is a function of x squared y minus y cubed right? So then del f is, we have a vector, del f del x, so 2x y, that one is 0. Then another del f del y, so you have x squared minus 3y squared. Okay. Alright, so okay, I end up this video with another definition, which we say f is called a conservative. Quite important terminology, conservative vector field. Okay, conservative vector field if there exists a potential function f such that f, capital F is equal to del f. Okay, so I just give you a definition for this video. Further discussion I will discuss in other. So here arise a quite important question. Yeah, from that definition, from that conservative vector field definition of the conservative vector field, arise a very important question. If you were given, let's say you were given a conservative vector function, f, can we find a potential function, let me write in full, a potential function f, or in other words, can we find, given f, can we find f such that this relation is true? Of course, for the conservative vector field, we have a condition for that. Okay, conservative vector field, we have condition for this. What condition? We will deal this with later, next video. So for now, thank you.